Thank you, Luke. Good afternoon, everyone. Kia ora koutou. So yeah, I'll be talking about this. This is work that I did with Claudia Chinadaisy and Jim McCowan, largely when I was a postdoc at Woods Hole, but now kind of carrying on. And I've put this image in the background up that I'll show you again without text all over it, but kind of embarrassing amount of my work over the last few years has been inspired by this single image. And what we're looking at is a Greenland glacier kind of off to the right as you look at it, and this kind of gray patch of fluid in here is what we'd expect from our subglacial discharge. So this is really sediment-laden fluid, which has risen up. It was released at the base of the ice as fresh water, has risen up the face of the ice face, reached the surface with all the sediment, which is why we can see it, and then eventually it sinks back down. And the reason we care about these is because they're associated with high melt rates. And although this image is taken from Greenland, and we often associate these flows with Greenland, and that's about as far away from the Southern Ocean as we can get, I will try and argue that the processes that we're looking at in these studies, and potentially probably these subglacial discharge plumes as well, are also relevant around Antarctica. So another couple of images. So this one's on the left, and this is what we tend to see in Greenland. So we've got these large glaciers, they come down. Unlike Antarctica, and this is going to be important, we tend to have vertical termini. So instead of a large ice shelf, we've just got a vertical ice face. And we either see, like we do on the right, this kind of suspended sediment layer at the surface, or in the left-hand case, we've got this iceberg melange in front of the ice, in front of the glacier, trapped inside the fjord. And that's just been pushed away in this kind of localized place. So that's basically our surface signature of our subglacial discharge. And you can see that the people from NASA wanted to put a probe in there, which sounds like a great idea to me. And again, the reason we care about these is because they're associated with high melt rates. So I'll talk briefly about how these things form, and then I guess make the case that they should form sometimes, at least in Antarctica as well. And then I'll look at two studies that we've done. The first is looking at basically the role of suspended sediment in these plumes. And then the second is going to be thinking about melt rate parameterizations. And at that point, I'm going to generalize a lot further as well, and not just think about, I guess, these subglacial discharges. So another difference in Greenland and Antarctica is we generally get quite warm temperatures in the middle of summer in Greenland. So we get widespread meltwater ponds forming along the kind of center interior of the ice sheet. So this is some people measuring these meltwater ponds. And obviously in Antarctica, it's a lot colder than it is typically in Greenland, and we don't get the same degree of ponding at a regular cycle. So eventually these ponds become large enough that they crack the ice and form these large crevasses, and that allows the meltwater to flow all the way through to the bottom of the ice sheet. And then from there, it's going to follow through these kind of subglacial hydrology, so this really complex system of channels, where it's eventually released, eventually flows underneath the ice sheet all the way to the grounding line, where it's released as this freshwater plume at the base of the ice face. And you can see that as it's kind of flowing under there, the schematic has drawn it, getting more and more turbid, carrying more and more sediment. And that's important for us, both in the role it has on the discharge plume, but also just as a way of visualizing. This image is kind of nice, although it's maybe unrepresentative of Greenland in some sense, because it's showing an ice sheet. And unlike this image, most Greenland glaciers do not have ice sheets. They have this vertical terminus that I've already mentioned. And this is one of the reasons that we don't see the same types of plumes forming in Antarctica. Because of the ice sheets that kind of extend for a long distance in Antarctica, we don't get quite as strong a subglacial discharge because the flow has to go along this very gradually sloping, basically horizontal ice face, and will probably intrude at mid-depth. Whereas in Greenland, it can just rise up to the surface. So that's one of the reasons we don't see the same types of phenomenon in Greenland. And the other, I guess, is that we have slightly different hydrology and that we don't get extensive ponding. But there is some other evidence that we get complex Antarctic hydrology and subglacial discharge plumes. So we don't get the same kind of nice visual pictures or photographs. But what I've shown here is mapping of a subglacial lake in Antarctica. So what they're doing is they're basically just looking at the elevation of the ice surface and seeing how that changes as a function of time effectively over, in this case, almost a decade. And this region that they've put in a big black circle where we've got this concentrated red color is what they've identified as a subglacial lake. So underneath, kind of however thick this ice sheet is, there's a region of liquid water that's just kind of sitting there. And we're seeing evidence that that's going to build up over time. So if we look at our height anomaly, first of all, we'll notice that it's very, very localized. So outside this black region, this circled region, there's no kind of coherent pattern and much weaker trends in how our elevation is changing. And if we look within this region over a kind of decade plus time frame, we see a gradually increasing height anomaly. This is over an area of about 260 kilometers squared. It's quite a large area that builds up over kind of a decade and then all kind of collapses in about 1 year. So this is showing us evidence that we've got this lake that's forming, building up slowly over time, lifting the ice surface as it does, and then all of a sudden, some pathway underneath the ice forms and that water is released, and then our ice surface collapses back down. The implied volume flux of this process is about 200 cubic meters per second, which is roughly equivalent to those discharge plumes that we see in Greenland. This is, I guess, for evidence, one of the larger subglacial lakes that was mapped in Antarctica. It's always good to use extreme examples, but hundreds of these different subglacial lakes have been identified and mapped. So really all of this is to say that although we don't see this clean surface expression of our subglacial discharge like we do in Greenland, we would expect subglacial discharge to occur. It's likely to be less seasonal and predictable and happen on a kind of more sporadic, chaotic nature. But once this water is released, there's kind of nowhere for it to go apart from to the grounding line and to form one of these plumes. And just as in Greenland, we'd expect that to be linked with elevated melt rates. So the reason we care about this is to do with melting, and I will use a slide just to kind of talk about. Maddie kind of did some work for me talking about this melt rate parameterization, which is widely used in situations where it may or may not be appropriate. But effectively what we're doing is we're parameterizing our melt rate by a drag coefficient multiplied by the flow velocity. This was Maddie's friction velocity that she talked about, multiplied by a temperature difference between the ocean and the ice face, and then some transfer coefficient. And again, Maddie did a great job of talking about this and described it as, I think, something like how efficient it is, how efficient the flow is at transferring heat, in this case, all the way to the ice face. And that idea of efficiency is going to be really important. And we'll have a similar equation for salinity, and then another equation that links the two based on the properties of ice. So this is going to be our first equation that we're going to look at. And then if we've got the subglacial discharge plume, our velocity is going to be the velocity of that plume. So we're going to couple this melt rate parameterization with a plume model. In this case, this will be the velocity of our plume. Capital B is our buoyancy flux, so effectively just how much fresh water we're releasing at the grounding line. And alpha is the entrainment coefficient. So the entrainment coefficient generally has a value of about 0.1. And this is relating or describing how efficient the plume is at grabbing ambient ocean water and dragging it into the plume. So we have these two kind of linked parameters here. We've got gamma T, our transfer coefficient, which is describing how efficient the flow is at getting heat and moving it to the ice face. And our entrainment coefficient, which is telling us how efficient the plume is at getting ambient fluid and dragging it into the plume. And obviously, since the ambient fluid is the source of heat and salt as well, we'd expect these two things to be kind of linked. So what I'm going to do is I'm going to present, I guess, two series of experiments. The first one is going to think about how alpha, our entrainment coefficient, might change as we add the sediment. And then the second one is going to be thinking about how our melt rate might change, since that's what I guess we really care about. So first of all, we're just thinking about suspended sediment and plumes. We can broaden this. We don't need to think about these subglacial plumes. We could also think about ash clouds like this lovely one in New Zealand. And all we're asking is, how does the suspended sediment affect the plume? So we've done some experiments, laboratory experiments. So this is a very sped up video of the experiment. It's very simple. This is our kind of filling box problem for those who are familiar with that. So we just have our axisymmetric or point source plume. It's rising up and it's filling some space with plume fluid effectively. And by tracking this kind of first front, this interface, we can get an entrainment coefficient of our plume. And what we're going to do, we can play this again. What we're going to do is we're going to test this for a variety of particle sizes. So all relatively small glass particles, about 50 microns, but a range of kind of particle sizes, which we'll characterize by a Stokes number. And then particle concentrations as well. And that will define by the ratio of particle buoyancy and salinity buoyancy. So all of these particles want to sink down, whereas the plume's rising up. In most cases, I will talk about one situation that's not like that. And if we think about this parameter, if it was 0, then we've just got our normal plume. And if it goes up to 1 effectively, then we've got perfectly offsetting particle buoyancy and salinity buoyancy. So we'll be within that range of 0 to 1. And we're going to see how the entrainment coefficient develops. And we don't need to watch it again. So this is what we get. So on the y-axis, we've got our entrainment coefficient. On the x-axis, our buoyancy flux ratio. So going from no particles to a particle concentration of about 2% by weight, if we want to think about that way. So at the source, that's maybe comparable to one of these subglacial discharge plumes. And regardless of our Stokes number, what we see is an increase in the entrainment coefficient by about 40%, maybe 50%. And for those of you who, I guess, haven't been thinking about entrainment coefficients, this is going to be a really significant impact on the plume. So if we're thinking about the velocity of this flow, or if we're thinking about the volume flux as it develops, this change in entrainment coefficient is going to be really, really significant. And I'll note here, I'm not going to show the results, but if we put this plume in the opposite direction, so in this case, what I'm showing, we've got our plume going up and our particles wanting to sink down. If we made them both in the same direction, so we turn the plume upside down and they're both sinking, we see no impact on the entrainment coefficient. So that's kind of not relevant to our geophysical case, but is an interesting asymmetry in what's going on. Or you could, I guess, think about this as if we had bubbles in our subglacial discharge plume, we wouldn't expect them to change the entrainment coefficient. So we can kind of understand this, and this is kind of getting down to a small scale. And basically what's going on, or we think is going on, so these particles, they have inertia, they have mass, and they don't really like spinning around and around in eddies, so they tend to cluster in regions where we have low vorticity. And we see this in all types of studies of particles in turbulence. So this one here, we're typically just looking at homogeneous turbulence, and we see these kind of filaments and clusters of particles. And if we get one of these clusters of particles that gets large enough, then its buoyancy can reverse compared to what's around it. We get convective instabilities, and that should lead to more entrainment. And this kind of explains the direction of the plume mattering as well. So the case we've been looking at is the one on the right. We're imagining this blue dot as a little particle cluster that gets really, really dense. It wants to sink down. It falls out of the plume, crosses that kind of turbulent, non-turbulent interface, then gets re-entrained into the plume. And each time it crosses that interface, it can provide a little bit more mixing. If the plume and the particles are going in the same direction, because the plume spreads as it develops, it doesn't get that chance to cross the turbulent, non-turbulent interface, and we don't see an increase in the entrainment coefficient. But really the point of the story is just that as we increase these particle concentrations, we're getting a higher entrainment coefficient. But what we're really interested in is melt rate. So we'll go back to these equations and we'll kind of work backwards. So alpha, our entrainment coefficient, has gone up by, say, 50% to make it easy. We want to think about how that's going to change the flow velocity, because that's our kind of first order effect. Our buoyancy flux hasn't changed. Alpha's gone up, so our flow velocity should go down. And then if we put that into our melt rate parameterization, it suggests that our melt rate should decrease. And maybe that's okay. But I kind of stressed at the start that our entrainment coefficient and our transfer coefficient are kind of similar. So our entrainment coefficient's talking about how efficient it is to bring mass or fluid volume into the plume, and our transfer coefficient is telling us how effective it is to bring heat into the plume. So we've got kind of two arguments that both seem reasonable, working in opposite directions. So it's time to do some more experiments. So these experiments, we're looking at ice melting. We've got, in this case, a two-dimensional ice face. So the same type of plume, but now instead of a point source, we've got a line source. Same particles, most things are kind of kept exactly the same. We'll change our particle concentration just like we did before, but this time we're going to measure the melt rate of this ice face. And I guess we're trying to see, does it increase or decrease as we add our particles? So if we look at the results, this is our melt rate on the y-axis and our buoyancy flux ratio on the x-axis. And what we see is fairly clearly, note this doesn't start at 0, this scale, is that our melt rate increases by about 50% and then appears to reach a constant value. If we look at our entrainment coefficient on the same line, we can kind of make these look how we like, but we can kind of see, or at least hopefully be convinced that there's some link between these two things. So our melt rate and our entrainment coefficient seem to be linked, at least to some point. We're not really sure what's going on beyond here, but I will note that these are kind of different systems. We've got an axisymmetric plume and a line plume, which, as I've mentioned, and they don't really behave in exactly the same ways. So there are some differences here. We don't expect perfect agreement, but at least what we can say is that our melt rate increases rather than decreases as we increase our particle concentration, which is suggesting that our transfer coefficient needs to change. So if we go back to our equations for the last time now, again, as we increase our particle concentration, alpha goes up and our velocity goes down, and our melt rate appears to go up. And the only way to make this true is for our transfer coefficient to also increase with particle concentration. And physically, this probably shouldn't come as too much of a surprise. They're kind of describing similar processes. We're looking at the efficiency of transport from the far field to the plume, or the efficiency of transport from the far field all the way to the ice face. So there's clearly a link here. So at this point, I want to kind of take another big step back and think, can we make inferences that are even broader than thinking about these particle-laden plumes? Because at the moment, we've been thinking about one system, but there's nothing magic about thinking about the presence of particles. And in fact, if we can go broader, that's going to be even better. And I guess maybe even more applicable to Antarctica, or the Southern Ocean, which is what we supposedly care about here. So what this is really built around is our entrainment coefficient changing, but there's a whole lot of things that can change our entrainment coefficient. So if we've got a point source plume or a line source plume, our entrainment coefficient would be slightly different. So if we think about our subglacial discharge coming from a singular point or from a distributed area, we should end up with different entrainment coefficients, and therefore we should think about whether we should have different transfer coefficients in our melt rate parameterization. Similarly, if our plume is dominated by the discharge flux, so if it's dominated by our subglacial discharge, or whether it's dominated by the buoyancy flux due to melting, that will have a very, very different entrainment coefficient and should probably have a very, very different transfer coefficient as well. And this is, I guess, before we even think about cases where we don't have a plume that's our driving velocity field, all the things that Maddie looked at and Kat's worked on as well, where we definitely need to start thinking about different values of the transfer coefficient. So the point really is that this idea of a universal transfer coefficient is never really going to work. We seem to have this direct link between our entrainment coefficient and the transfer coefficient, but there's a whole lot of other things that are going to change the value of that transfer coefficient. And by thinking about it as how efficiently is the flow transporting heat or salt to the ice face, I think that starts to become a better framework and maybe more clear. So I'll leave things there. The three main points that I guess I want you to take away: suspended particles increase the entrainment into turbulent plumes. This is going to be relevant for us whenever we have these particle-laden plumes, but hopefully it's more broadly relevant. Through that, it also increases the melt rate of the ice face. And by combining these kind of two observations, we can kind of demonstrate that melt rate parameterizations should, I guess, A, consider sediment concentration, but really, and more importantly, anything else that could plausibly affect the entrainment coefficient of the flow, because that's going to change how much transfer we get. I'll leave things there. Thank you.